something else. So you would load up this sample tray with, let's say, 16 of your pressed powders that you want to analyze, and you're going to choose some spots. So what you can see is those little discolored spots on some of the pressed powder pucks. That's what a post-analysis looks like. We're only removing, 100 nanometers of material during this analysis. It's very, very fine material removal, so it's not really destructive. We call ourselves pseudo non-destructive, but you're still able to see where you analyze just because of the way it diffracts the light, but it's not actually removing much material at all. So anyway, you choose your spots that you want to analyze on your puck. Maybe you want to do the whole thing. Maybe you want to do 3 small areas. It doesn't matter. The next thing you're going to do is press go. And this is a small video of what it looks like to actually analyze the tool. So what you're seeing is the crosshairs are going to be where you are on the sample. And the upper right-hand side is a live camera view. And on the left-hand side of the screen that's now pulled up here, this is our mass spectrum. So this is a 316L stainless steel. So obviously we're going to see lots of molybdenum, lots of iron, lots of tungsten, whatever it may be. We get the entire table. We can also track this in time to say, is this a very homogeneous sample, or are we seeing lots of spikiness in the signal that we need to assess and look at afterward in a post-analysis map, let's say, to look at whatever the entire picture of what's in here, not just the bulk composition that you get when you digest it in a bunch of acid, but also giving context to your chemistry. So one of the things we like to say is this is chemistry at the scale of printing, right? Our spot size here that I didn't mention is adjustable from 5 microns to 200 microns. So you can get a very fine analysis of an individual particle of your powder, or you can average a lot of particles together and do a big map to get a more statistically representative average, especially if you have something that's a mixed powder. So from this mass spectrum, we have to make it mean something, right? All we did was we have all of these peaks, and we need to now integrate those peaks, apply a calibration curve to it, and say, can we get something useful out of it? So I'm going to walk you through a few case studies here. So we're just going to stick with this 316L example that you just saw on the last screen, and we're going to quantify the composition of the virgin and recycled stainless steel powders. So the first thing we're going to do is we're going to look at a mass spectrum. Let's get familiar with this. The x-axis, this is going to be mass, right? So carbon's going to be much lighter than iron, which is going to be much lighter than molybdenum, going to be much lighter than tungsten. So that's the way to think about this. And we are separating out all those masses in time, right? And the intensity on the y-axis is how much of that element, so you have 56 iron being shown here, how much of that element hit the detector, can we integrate and make mean something? So one of the really important things when trying to create a new technology to, again, remember, fundamentally change the experience of what it's like to use a mass spectrometer is that we needed to take away the algorithmic complexity and any sort of multivariate space. We needed this to be a very linear process that we could be the analytical chemist for our customers. And all you need to do is choose the spots to analyze, press next, apply a calibration curve, and you're done. And one of the advantages to the way our technique works, and if you guys have questions, again, please ask for clarity on maybe some more of the fundamentals in the Q&A session. But one of the advantages our technique gives us is that we are isotopically correct. So for a quick refresher, all elements have isotopes. So for example, boron has 2 isotopes, boron 11 and boron 10. And they're shown in these known ratios of 80.1 and 19.9. And as you can see by our analysis, we got 80.8 and 19.2. So it's isotopically correct ratios. And you're thinking, why do I care? I don't want to think about isotopes. And that's the exact point, is that you don't have to. Because what we're able to do automatically is look at boron, look at these 2 isotopes and say, that is definitely boron. I'm going to verify that element for you. And I'm going to know that I'm going to apply a calibration curve to boron, and you don't have to think about it. So for example, just to give you some context of sensitivity here, this boron was 10 part per million in the sample, carbon was 210, and nitrogen was 670, and you have 50 part per million oxygen. So you're able to see these very, very low elements in this stainless steel at the same time seeing the big iron peak in the other screen. So just showing sensitivity, showing breadth of elements, isotopic correctness allows us to be the analytical chemist and you to get the data you need and move on with your life. So the first step of doing this is we need to prove that we get the right answer for everything that we analyze in the sample. So these were certified values for a 316L powder that we quantitated with an unknown, compared them to other techniques. In this case, it was ICP-MS and inert gas fusion and XLRAF. So it was 3 techniques that were combined together to make this full spec list. And we analyzed every element in one pass with one tool and got the same answer. And this is everything from really hard things to do like nitrogen and carbon to chromium and cobalt, and across a huge dynamic range again. So we get the right answer. We've done this for 316Ls to all sorts of other stainlesses to coppers and aluminums and niobiums and nickels, like I mentioned. We really don't care what it is. As long as it's solid and flat, we'll shoot it, we'll get the right answer, and we're going to enable you to operate faster. So one of the big things in additive manufacturing, as I'm sure everybody on this call is aware of, is obviously powder reuse. And one of the biggest factors in powder reuse is, did I expose oxygen to it? Did it oxidize, or did it get contaminated from the last batch of powder that I had in the machine? So we wanted to look at this, and we're going to stay with 316 so that we just keep getting familiar with this mass spectrum. We wanted to look at recycled versus virgin. And we also wanted to say, well, can we take that recycled and virgin and then also like artificially oxidize it and see a difference as well? And this is really important because sometimes this can be very difficult to do or time consuming. And a lot of companies making parts will just not reuse powder, especially for parts that require certain control limits, because it's not known well enough. So what we're enabling is a whole new study of what is that limit of oxygen that I can keep reusing powder and keep remeasuring and recertifying within a few minutes, so that I'm not just throwing out maybe perfectly good powder because we're not sure of what to do with it. So you can see here is looking at oxygen 16. So this is the major isotope of oxygen, is that in the blue, we see the virgin powder has much less oxygen 16 than in the recycled. And this is what we would expect. And the question is always, well, how much is too much oxygen? Well, now we're giving you a very fast tool to start defining that for each of your individual processes. And if we take that one step further, this is now quantitated oxygen. So we took that curve and we said, okay, this had 3,000 parts per million oxygen in the recycled and about 1,000 part per million in the virgin. So about a 3x change in oxygen just from virgin to recycled powder. And what we wanted to show is that we could actually see this even on a scale where if we just left this powder out for a little bit, can we tell that it's been oxidized even more? How sensitive are we? And sure enough, we aged this powder just by leaving it out. We did a few other experiments and different things as well, but for right now, we'll just focus on oxygen and say, yeah, this technique can really be very sensitive to oxidation in these powders, and we can use this as a tool for providing a spec of this is okay to reuse, this is not okay to reuse, or this is okay to reuse, but only in this context. So Massbox can not only tell you your bulk chemistry of, yeah, everything's still okay from the aluminum, iron, and nickel in there, but also as I'm printing with this powder, I can keep reusing it. And you can take that recycled powder part after you print with it, put it in the Massbox, and make sure that the oxygen in the finished part is also to spec as well. So every part of your process control, Massbox is here to ensure that you're going to get quality